So thank you for inviting me to present my research here. And so I'll tell you today about a talk that I constructed for the general public that basically will start talking about quantum mechanics and lead that into some examples of how we use quantum mechanics in our research in the Getman group. So we'll start with a story about a meme. So if you're like me, maybe you've been looking at a lot of memes over the pandemic as a way to pass the time while you're home alone or home in isolation. So this particular meme is about COVID, so I'll read it to you. So it says, we all have Schrodinger's virus now. And it says, because we can't get tested, but I'll say one of the nice things about being at Clemson is because we can get tested. So we have access to free and easy COVID testing. But if you're not so lucky to have access to that, maybe you can't get tested. So because we can't get tested, we can't know whether we have the virus or not. We have to act as if we have the virus so we don't spread it to others. We have to act as if we've never had the virus, because if we didn't have it, we're not immune. Therefore, we both have and don't have the virus, thus Schrodinger's virus. And then it says, if you don't understand this joke, you're never allowed to talk about science again. So I don't like this last statement in this meme, and I'll take the next couple of slides and share with you why. So basically, this meme is a play on a thought experiment called Schrodinger's cat. So Schrodinger's cat involves superposition of quantum particles. So by superposition, what this means is that quantum particles can exist in multiple different states simultaneously. When they come into interaction with each other, they may collapse into a single state, but in isolation, they can exist. And in fact, even once they interact, they can exist in multiple states simultaneously. So talking about a quantum particle, that's a particle that's either really, really small, for example, a subatomic particle, or a particle that moves really, really fast, so approaching the speed of light. So as an aside, quantum particles that we've all probably heard of are, one example of that is electrons. So electrons are quantum particles. They have discrete energy levels, so those would be the atomic orbitals, and they can exist simultaneously in multiple energy levels. When I say exist simultaneously, really an electron we don't really think of an electron as being in one place at one time. We think about the probability that it's in a variety of different places. So there's never a 100% probability that an electron would exist in a particular orbital. There can be a very dominant probability that it exists in a particular orbital, but there's still finite probability that it doesn't. So by that, that's a concept of superposition, that the electron is existing in multiple energy states simultaneously. So pretty different physics than humans. I, for example, am sitting on the second floor of a building. I cannot simultaneously be sitting on the second floor and the ground floor. I can only exist in one state, whereas an electron can be multiple. So the Schrodinger's cat thought experiment wanted to illustrate this principle of superposition and how at the time it was being misinterpreted. So at the time, people were saying that the particles are existing in multiple states simultaneously, but then they will collapse into a single state upon observation. But it wasn't really observation that causes the particles to collapse into a single state. There's other phenomena that can contribute to that, and one is interaction with another particle. So long story, getting there. So the Schrodinger's cat thought experiment, what Schrodinger came up with to illustrate this. So imagine that there's a cat, and the cat is in a box, and inside the box also is poison that can be released by decay of a radioactive material. So this is maybe not the happiest story. So the decay of a radioactive material would release subatomic particles. If we believe that superposition, that the particle would exist in multiple states simultaneously until it's observed, this means that the cat inside the box is simultaneously both dead and alive. And then once you open the box to observe whether the cat is dead or alive, then that collapses into one result. So the cat is either at that point dead, or the cat is alive. And the thing that made the cat be dead or alive was you opening the box and observing it. But this is not the case. This is the whole point about Schrodinger's cat, is to point out the absurdity of this, because it's not the observation that kills the cat, it's the interaction with the poison. So let's go back to the meme. So what the meme is saying is, in the event that we can't observe whether or not we have the virus, then we have to assume that we simultaneously have it, and we don't. So this is a play on superposition, the principle of superposition. We both simultaneously have the virus and we don't. But the whole point of Schrodinger's cat was that observation is not the sole cause of collapse. So its interaction with other particles causes collapse. And also that superposition is complicated, even confusing scientists. So the thought experiment of Schrodinger's cat was developed in order to demonstrate not only to non-scientists, but also to scientists that the principle of superposition was being misinterpreted. So I think that the moral of this story is understanding superposition should not be prerequisite for discussing science. So I would like to fix the meme and says, rather than if you don't understand this joke, you're never allowed to talk about science again, I'd like to fix it so that it says, if you don't understand superposition or any aspect of quantum physics for that matter, join the very large club. So for me, I accept quantum mechanics. I see it working in my research, and I see that it's able to explain behaviors of quantum particles like electrons, but I find it confounding. I find the principle that a particle can exist simultaneously in multiple states, I find that to be confounding. And the reason for that is because that is not the world that we as humans are observing. So we aren't observing phenomena like that. So it's difficult. It's difficult to understand. So let me tell you about another story about a cat, and this one is slightly happier. It's a lot happier, but you have to wait to get to the happy part. It takes a minute. So this is my daughter Anya, and she's almost 10 years old, and she's holding her cat Raven. And a couple of years ago, Anya went on a trip with her schoolmates to the beach, and it was a class trip, so she stayed over at the beach with her school. And then a couple days later, we drove over to the beach to pick her up and bring her home. And while we were gone, Raven disappeared. And so we got back and Raven was gone, and she didn't come back. And we thought, she must be lost or someone else took her in. Well, we live a little bit outside of Clemson, about 10 miles. Turns out Raven had walked 8 miles back towards Clemson. Who knows why, maybe trying to find Anya. She was found by someone who she had stopped by their place to eat, and the person was feeding her. And so eventually the person took her to the vet, and she has a microchip. So they scanned her and called us, and everyone was very happy that Raven came home. But of course, at that time, Anya was maybe 8 years old. And, this was devastating that her cat had left. So I spent, as a parent may do, a lot of time on the internet reading about the likelihood that we would get this, that Raven would come home. And the internet actually says that up to 80% of cats who go missing are ultimately reunited with their owners. There's many theories as to how cats ultimately end up finding their owners. And lots of stories on the internet about cats being reunited with their owners, which is good. One of the theories I found interesting and very coincidental was that there's the bond between a cat and the cat's owner causes quantum entanglement between particles in the cat's and owner's brain. So you form this bond with your cat. Something in your brain becomes entangled with something in the cat's brain, and because of that, cat goes missing, but ends up finding it. So that brings up another property of quantum particles. What is quantum entanglement? So quantum entanglement is when the behaviors of one quantum particle depend on the behaviors of another quantum particle. So this is an inherent property of quantum particles, and it's as normal to quantum particles as gravity is to us. For electrons, so electrons are quantum particles, the quantum entanglement, the property of quantum entanglement is called electron correlation. So correlation in electrons basically means the behaviors of one electron influence the behaviors of all the other electrons around it. So I don't really have a good way to conceptualize this other than if you've ever watched a flock of birds, like a big swarm of birds, and the birds kind of move together, right? So they're responding so all the birds are responding instantaneously to the movements of all of the other birds. So that's kind of like those correlated motions of those birds are kind of like correlated or electron correlation, the correlated behaviors of electrons, with the one exception that with the birds are staying in a flock and staying together. Electron correlation actually makes electrons want to stay far apart. There's actually a hypothesis that all of the electrons in the universe are correlated, which means that any electron in the universe changes position or changes state, that has an influence on all of the other electrons in the universe. So I think that's a pretty confounding hypothesis to conceptualize. But hypotheses are hypotheses. So that leads me to my first key point in this presentation. Electrons and, in general, quantum particles are complicated. So they follow different rules than we do. They follow rules that are not apparent to us and that we in our daily lives are not observing. So the issue here is if we want to study materials, so my group, we study materials in order to try to make better materials. And to do that, we have to learn how materials function. And material performance depends on the behavior of electrons. So if we want to do materials research, then we have to understand these confounding behaviors of electrons. So I want to tell you a little bit about some of the examples of materials that my group studies. So one example is magnetic materials. So magnetic materials, specifically we're looking at ferrites, which comprise iron and other metals. And they're used in a variety of applications, spanning from biomedicine to electronic devices. Here are some examples of how they're used in biomedicine, for example, magnetic resonance imaging, and also magnetic hyperthermia. In this case, the magnetic materials would be used to generate heat that could target, for example, cancer cells. And all of this performance is due to the magnetic properties, which are caused by unpaired electrons within the material. Another type of material that my group works on a lot, so the rest of this presentation I'm going to talk about, these types of materials are catalytic materials. So catalysts are materials that promote chemical reactions. Just about everything we touch every day has seen a catalyst at some point in its development. 90% of chemicals by volume are produced by catalysts, and catalysis contributes 35% to the global domestic product. So catalysts are pretty important materials. So some applications of catalysts, one is food. So production of fertilizers is one of the largest uses of catalysis in the world. I believe 1% to 2% of the world's energy goes into producing fertilizers via the catalytic process called the Haber-Bosch process. Also, the production of food, both natural and artificial, and food storage is driven by catalysts. A big use of catalysts is in transportation. For example, gasoline is a large use of catalysts is production of gasoline. And another use of catalysts is cleaning of emissions from vehicles. So for example, if you drive a gasoline car, then you probably have a catalytic converter in your car. What that is doing is converting unspent fuel and also carbon monoxide and NOx compounds into less harmful compounds. Another use of catalysts is in the creation of products, for example, plastics, both in their creation and repurposing, as well as creating chemicals, polymers, etc. Again, 90% of chemicals by volume are produced by catalysts. Another example is in life and health. So for example, every living thing comprises enzymes, which are natural catalysts found within living things. Pharmaceuticals are also made by catalysts, as well as a variety of other examples. So really, catalysts and catalysis are ubiquitous to our society. So why do we want to study catalysis? So the American Chemistry Council reports that member companies, so companies in industry, increased their efficiency by over 17% and reduced greenhouse gas emissions by over 18% between 1992 and 2013 due to the adoption of catalytic processes. So catalytic processes are making industry more efficient. However, they are still highly unoptimized, and this results in larger than necessary energy requirements. So given the ubiquity of catalysis to society, there's significant potential to improve sustainability by optimizing catalytic processes. So if we want to optimize catalytic processes, we need to know how these catalysts are functioning. So what a catalyst is doing is promoting, it's helping a chemical reaction to occur. So most chemical reactions require energy, and the amount of energy that's required is that necessary to break chemical bonds and form new ones. So a very common type or class of reaction that a catalyst would be used in is an oxidation reaction. So I'm showing here a very common oxidation reaction. This is carbon monoxide reacting with molecular oxygen, which is the type of oxygen that's in air, to form carbon dioxide. So carbon dioxide, of course, is a greenhouse gas. It's not a desirable chemical, but carbon monoxide is toxic. So one way to get rid of carbon monoxide is to oxidize it to carbon dioxide. And in fact, this is one of the processes that a catalytic converter would carry out. So in the absence of a catalyst, this is a very energy intensive process. It requires a large amount of energy input for this to happen. And the reason for that is because it takes a lot of energy to break this oxygen molecule into two oxygen atoms. And to be honest, that's a good thing. That's good for us because we need this oxygen. Molecular oxygen is very important to life. And the world would be quite a different place if this oxygen molecule weren't so stable and it could readily be broken into oxygen atoms. So it's a good thing that this is an energy intensive process. But if we want to perform an oxidation reaction, for example, carbon monoxide oxidation, that is not so great that it's so energy intensive. Unless we have an effective catalyst. So for example, a platinum catalyst will readily break the oxygen-oxygen bond, break the oxygen molecule into atoms and allow them to react with carbon monoxide to form CO2. So this is actually a simulation of that happening. So this red here is an oxygen molecule and the gray is a platinum lattice, and the platinum will readily bind with the molecular oxygen and break it apart, creating atoms that can then be deposited on the carbon monoxide molecules to form CO2. So the platinum catalyst is providing a lower energy route, a less energy intensive route from reactants to products. One issue here, though, is that platinum is really expensive. So even when we are able to find catalysts that drastically reduce energy requirements, there becomes a challenge of finding catalysts that can be used in a variety of processes. So the amount of platinum on Earth is limited. Platinum is very expensive. Hence, all of the reactions that platinum could catalyze, it's cost prohibitive for many of them. So for example, one example where the price of platinum inhibits the broader adoption of a technology is fuel cells. So one reason that we don't see fuel cells being more commonplace is because of the expensive noble metals that would be required to perform the chemistry. So the strategy to that is to try to identify materials that perform similar to platinum or more expensive materials, but cost less money. So that is an aim of my group. We want to use, in fact, molecular simulations to understand how catalysts function so that we can design better materials. And to do that, we need to understand electron behaviors. So catalysis is essentially the study of electron behaviors. So the breaking and forming of chemical bonds is essentially electrons interacting with each other. And so learning how to direct catalytic performance requires simulating electrons. So that is what my research group does. We study catalysis by simulating electron behaviors using quantum mechanics. And this is a recent picture of my group. So quantum mechanics simulations. So this is what my group does. We perform quantum mechanics simulations in order to learn about the chemistry behind different catalysts of interest. So these simulations are challenging, and one of the reasons why is that they have to account for electrons and their confounding behaviors, such as superposition and quantum entanglement. They're also very detailed. So you've probably seen the Schrodinger equation at some point. Solving this thing is pretty challenging. And so because of that, we're definitely not doing those simulations by hand. We use computer software to do them. And the software that we use can't be used, or it won't work on a laptop like mine. We have to use a high performance research computer. So we use Clemson University's Palmetto supercomputing cluster, which is many, many, many computers tied together with lots of RAM and storage space. And so this allows us to perform our simulations. And I'll say another reason why it's great to be at Clemson is this Palmetto supercomputing resource. So a lot of universities have access to computers such as this one, but ours is actually one of the best in the nation. So the last I checked, the Palmetto supercomputing cluster is the 5th nicest supercomputer amongst public US academic institutions. So the 5th nicest in the nation for public colleges and universities. It's faster, last time I checked, than Amazon Web Services. So very nice computer. Even on this state-of-the-art computer, though, to do one of these quantum calculations and account for all of these confounding behaviors of electrons, a single calculation takes at least hours, if not months. Some of the calculations that we do in the group take months to figure out from start to finish. And over the course of time that I've been doing molecular simulation research, catalysis research, I've had simulations that have taken almost a year. So pretty challenging to do. So some of the problems that my group has looked at, some of the catalytic problems that we've looked at using quantum mechanics simulations. One, the goal was to design catalysts that would oxidize butane into butanol. So this is butane and this is butanol. So this reaction has applications in the fuel industry, also the pharmaceuticals industry. A challenge to this reaction or to this catalysis problem is trying to find a material that balances both activity and cell activity. So making a catalyst that is going to actually work, it's going to do this conversion in a time scale that would be of interest to industry, but also cell activity. So we want to make butanol, but there's a lot of things that you convert butane into. So how do we make butanol and not anything else? So what we found, we need a catalyst that has just the right affinity for both hydroxyl groups and atomic carbon. And we identified that catalysts comprised of copper and palladium are promising for that, to balance out all of these various phenomena. Another problem that we looked at, so this is a large, outstanding problem, is finding catalysts to convert natural gas to higher value or easier to transport chemicals. So this is, trying to convert, like natural gas is comprised mainly of methane and ethane, and we want to be able to convert that to something more valuable or something that's denser and easier to transport. This requires a really highly effective and targeted catalyst. So this is trying to identify catalytic materials to perform this chemistry has been something that researchers have been trying to do for decades. And one of the conclusions is that it's going to take a really highly effective and targeted catalyst to do that. So we're going to really have to engineer a catalyst with really specific properties to be able to do that. So standard catalysts are not capable of carrying out this chemistry. One of the things that we found is that catalytic performance is intimately tied to electron spin. Spin is another one of these confounding behaviors of electrons that has origins in quantum physics. And our finding was that catalysts comprised of nickel and cobalt are promising for this reaction. The third problem that my group has been looking at, and we've been looking at this problem for the entire 9.5 years that I have been at Clemson, is to learn the influence of solvents on catalysis. And the reason that we're interested in this, so there is a major drive in industry to create processes that are less energy intensive. So one way to decrease the energy requirements of a process is to operate it in liquid conditions rather than gas conditions. So to do that, you would operate your catalytic reaction in the presence of a solvent. So this creates a significant challenge because once you introduce a liquid solvent into your chemical reactor, you're introducing a lot of molecules. So a liquid is very dense, whereas a gas is less dense. The density of molecules means that there's a lot more molecules around, and all of the molecules are doing different things. So what are the different molecules doing that influence catalytic behavior? And how do we deconvolute the various phenomena that are occurring in the catalytic reactor? So one of the challenges to this work is that it requires multi-scale modeling, which means it requires quantum plus other types of physics to carry out. And basically what we're trying to understand is how the solvent is influencing the catalytic phenomena based on the type of interface that it's interacting with, And our conclusion so far is that the solvent behavior can be predicted based on the hydrophilicity of the catalyst. This means, you know, if you have a water solvent and water really likes to bind to the catalyst interface, then it will have different behaviors than if water doesn't like to bind to the interface. And that probably seems, you know, pretty obvious in hindsight. But it's taken a lot of modeling to be able to extract exactly the different phenomena that go on at different types of catalytic interfaces. And I'm omitting a lot of details here, but it just goes to show the complexity of the problem when you have so many molecules and had so many electrons involved. So that's another key point. Simulating the behaviors of electrons and also simulating material performance is challenging. So not only do you have these confounding behaviors of electrons, but you've got a lot of different phenomena in play, particularly if you're looking at catalytic reactions that involve a lot of molecules and hence a lot of electrons. The other part about it, though, is that it's fascinating. We can really tease out a lot of interesting phenomena when we look at the molecular level. So the simulations that we do, the quantum simulations, allow us essentially to watch what is happening at the level of molecules. So with that, I will summarize. So there's significant opportunity to improve manufacturing efficiency and reduce greenhouse gases through rational design of materials. In part, this involves using computer simulations to learn how materials function at the electronic level. Electrons are complex particles that are governed by quantum mechanics, which itself is confounding, which makes those simulations challenging yet fascinating. And then for some reason, people have tried to explain quantum phenomena using cats as examples. So with that, I'll leave you with some pictures of cats. So these are my 3 cats. This right here is Howard. He is he's going to be 12 this year. He's a tabby cat. This is Raven. She's the one who took the journey to Clemson and luckily was found. And she is probably just turned 3. I mean, we don't know the exact birth dates of any of these cats, but she probably just turned 3. And this is Stout. So Stout will turn 3 in a couple of months. Interesting story about Stout. When Raven walked to Clemson, we thought we found Raven, and so we trapped a cat that we thought was Raven. In reality, it was Stout. So we added a 3rd cat because of that journey, which also is the story to motivate the property of quantum entanglement. So with that, I will open the floor with for questions, and thank you for taking the time to attend this talk. So the people in the audience all know me. So it's my student and 3 of my closest friends. So.
So does anybody have any questions? It was a great talk, very fascinating. Yeah, it's something that's so difficult to wrap your mind around, for sure, how something can be in one place. And I always kind of thought it was that they were going so fast that you couldn't predict where they were. But it sounds like you're saying they actually can be in multiple places at once, which is really, yeah, it's just hard to wrap your mind around.
Yeah, I don't know that I fully grasp that, because the other argument is that you can't precisely locate an electron, right? So you get these pictures of the orbitals, which the orbital has volume, and the volume is significantly larger than the electron itself. So, you know, the way that you would think about that in a classical picture would be, you know, the electron is zooming around in this little volume, but in reality, that's not even really true, right? So I don't know how to think about that, whether, you know, you don't really, do you conceptualize the electron itself or do you just say this is the region that it is in, and you won't really know until um, it bonds with something or something else, where it was.
Okay, great. I wondered too, I noticed that NASA was one of your funders, and I wondered like what kind of work you're doing, what kind of research you're doing for NASA.
That was a fellowship that one of my former students, a PhD fellowship that one of my former students has. He actually is now a research physicist at NASA. I When he was in the group, he was working. It was the aqueous phase work, looking at fuel cells. I don't remember precisely what he is working on right now, but it has to do with various material properties. And then other research in our department that is going on that's related to work for NASA involves, for example, converting CO2 into something useful or producing oxygen from waste or things like that.
Okay, great. Thank you. Anybody else have any questions before we wrap it up? Okay, if not, thank you again, Dr. Getman, for speaking. We're going to post this on our YouTube channel, and I'm sure many more people will be able to listen to your talk there. I did want to let you all know that the next Tiger Talks, and this is actually the final one for the spring, will be May 13th, same time, 6:30 to 7:30 p.m. And Dr. Carlos Garcia will be speaking. He's a professor of analytical chemistry at Clemson, and the title of his talk is Turning Paper into Chemical Sensors. So once again, thank you guys for being here. Thank you, Dr. Getman, for your talk. We really appreciate it. And that is all for tonight. I hope you guys have a wonderful evening.